And I put on my glasses today, so let's hope for the best. I can see sort of like 30 centimeters away, but if it's really close, I just can't see anything. Terrible. Yeah, I guess. Yeah, I guess. So I can see, and I almost know all of these notes by heart. So it's not that hard, but okay. So we have double angle identities. So what's the purpose of these identities? What are we gonna do with them? The same purpose and the same goal that we have used for the previous ones that we've done in lesson 1 and 2. We have new equalities that's gonna help us calculate values for angles for different functions at the ones that we don't have in the unit circle, right? So imagine here being 2 times 15, right? So you would just use that to calculate the value of sine of 30. And that means the 15 would be in here. So if you ask to calculate the value of 2 times sine of 15 times cosine of 15, and you don't have access to the calculator, you would have to say, okay, this whole expression equals that. All I have to do is 2 times 15 inside this sign and calculate now sine of 30, right? So one side of the equality is better than the other one, so we have to recognize which one it is and then move away from what we have to something that we can use without a calculator. And I included in this set of notes some proofs for all of these identities. A double of something is just the addition of the same thing. So if you think about this double angle as being theta plus theta, that's being sine of the sum, right? So think about this one being alpha and beta, and then you'll have sine, cos, cosine. And then this becomes exactly the same term. They're just in a different order, right? It's just commutative. That means you have 2 of the same thing. So 2 times sine of theta, cos of theta. And the same thing can be proved for every single other one of these identities. Now we have a cosine of double angle as well. And if you do the same approach of proof like before, we're going to end up with this main formula for cosine of theta. I'm going to call this one number 1. So cosine of 2 theta can equal to cos squared theta minus sine squared theta. Now, individually, if I want to have a formula for cosine of the double angle, just in terms of a sine function, I can replace cosine squared theta using the Pythagorean identity, 1 minus sine squared theta, and then put the like terms together, and I'm going to end up with that. Okay, that's still the formula or a formula for cosine of the double angle, but only uses sine. Okay, this one uses both cos and sine. It may be useful in some situations. And this one only uses sine. Okay, both of these ones are in your formula sheet, so you don't have to memorize them, but you have to be aware of the multiple ways you can do cosine of the double angle. And I can also do in the main one, in the very principal, original one, replacement for sine squared theta in this case with the same formula, the Pythagorean identity, replace it with 1 minus cos squared theta. And when I do so, and you can read all of that, you're going to end up with a formula in terms of cosine only. So it's going to look like this: 2 times cos squared theta minus 1. And similarly, we're going to have, this is going to be our third one. And we're going to also have a tangent of the double angle, 2 times tangent of theta, 1 minus tan squared theta.
First one, the sine, 2 times theta is not squared like the other ones.
Which one?
The top one.
That's how it works out to be, right? Because we apply the sum formula, and then it just becomes all of them are single one, and the thing is squared, right? And it's just, yeah, but it doesn't work like that for cos, because remember the cosine expansion for cosine of double angle is cos, sine, but it was different angles, so you couldn't put it together with a square. but not because your alpha and your beta in the sum formula are the same angle. When you end up with cos, cos is cos of the same angle, right? Since you can just combine them together as a square, right? So it just becomes that. Make sense? Sorry. Well, you don't have to. This is just for you to see where it comes from. This is a formula itself, but that's where it comes from. It's a great way to look at them sometimes when you see where they're coming from. It makes more sense. So we're gonna look at exact values using double angle identity. Formula sheet. Beth, do you have a formula sheet? There's some on the purple tower and on the third row there. You can grab one for yourself. So, sorry. Oh, on the side. Oh yeah, that's a filled out in a circle. Yeah, you like that? Oh, that's okay. Yeah, she'll be okay. So, given theta is in quadrant 3, and sine of theta is equal to -1/3. Find the exact value of sine of the double angle, a tangent of the double angle. So the first one, if you're asked for sine of the double angle, and usually for me, at least for any kind of problem solving, I would always start with something that I know about the question. So is it a formula? Is it a given that's going to give me some hint how I'm going to deal with this question? Even the idea that I have to do exact value, that means I cannot touch my calculator, right? So I have to use something that's going to allow me not to use my calculator. And at this point in time, which you know, X, Y, R, that's going to allow me to work with exact value without the calculators for trig functions. Or sometimes just a unit circle, right? With theta R and the quadrants and so forth, right? So I'm going to put all of those things together in my head or on paper, and I'm going to design a plan to see what I'm going to do. But for these types of questions, when you have to calculate sine of the double angle, sine of the subtraction, addition, you have formulas for them. You have identities, right? So I would start with that. What would it mean to calculate sine of the double angle? Okay, when the angle is not given, right? Well, I just have to do 2 times sine of the single angle theta times cosine of theta. So if I want to calculate this, I would need to know the value of sine of theta, and I need to know the value of cosine of theta, and I just have to multiply them times 2. Sine of theta is given to me, right? I already know what sine of theta is, -1/3. But cosine of theta is not given to me. So my work is, given that sine of theta is this, find another value, right? Cosine of the same angle. Well, I know how to calculate that because that's an X, Y, R problem. So sine of theta is -1/3. Sine values are negative in quadrant 3 and quadrant 4. That's Y, and that's R, not X. And then I want to narrow down the quadrant. It says given theta is in quadrant 3, right? So I already know my theta is in quadrant 3. I don't need quadrant 4 at all. But the negative is giving you possibilities. That means I have to find x squared using the circle formula. So now x squared equals r squared minus the other one squared. X squared equals 3 squared minus 1 squared. X squared is 9 minus 1, which is 8. square root of both sides. X is equal square root of 4 times 2. It was square root of 2, that's right. And that's just writing a root as a mixed root, because some of the numbers in that factorization can be factored out by doing the root of that number, right? Root of 4 is 2. So after you find all of your variable x, y, r, you can calculate any value you need, right? So that's one of the questions that you had in your test in unit 4 too, right? That was sometimes difficult. I think it's the first one in the long answer. There's your formulas using y, x, and r. And then if you ask for cosecant, what do you have to do with this? Just flip them. It's r over y. If you have to do secant, r over x. If you do cotangent, x over y, right? So we need to do the cosine. So cosine of theta in quadrant 3 is going to be positive or negative? Negative. And it's going to be x over r. So 2 square root of 2 over 3. So it's negative because we know theta is in quadrant 3. Are we done with this question? Did the question ask us to find cosine of theta? No. The question asked us to find sine of double the angle, double that, right? So for finding that, we needed cosine of theta, right? Intermediate step. So now we have it. All we have to do is plug and calculate. So sine of 2 theta is 2 times the given sine of theta first, negative 1/3, and then negative 2 square root of 2 over 3, which we calculated for cosine of theta. Negative times a negative and a positive makes it a positive final answer. And then we have 2 times 2, which is 4 square root of 2, and then 3 times 3, which is 9. The next one is tangent of the double angle. Tangent of 2 theta. Now I don't have to do a lot of work for the second one because I already know the x, y, and r for this theta, right? From the first part, the part A. So tangent of the double angle. I don't have these formula memorized, guys. Just look at them, okay? Find them in your formula sheet and know which one is which, okay? Now, of course, after you do a lot of practice question, you will remember them, you know, a little bit. But as soon as I take a break, like 2 weeks in between class, I don't remember. My brain doesn't hold something like this because it's not important to hold them on to, because you are given them, right? So just try to memorize only the things that you need, not the ones you don't need. So we want tangent of the double angle. So 2a is written in your formula sheet. So 2 times tangent of a, 1 minus tangent square of a. So let's copy that. 2 times tangent of theta, 1 minus tangent square theta. So we said we calculated what x was, y and r were given. So y is 1, r is 3, x was 2 square root of 2, right? This one because it's bigger. Okay. So for tangent of theta, in quadrant 3, remember we are in quadrant 3 with our angle theta, it's going to be positive for tangent values. Tangent is y over x, right? So this is the formula sheet again. You don't have to memorize them. They're right there. So y is 1, x is 2 square root of 2. Now it's really up to you if you want to rationalize this one or not. Sometimes it's easier if you rationalize and it makes the next calculation a little bit easier, but sometimes it makes it more complicated, okay? So you have to gauge it from question to question. When you do have squaring in a calculation, you'll know that the square root will disappear anyway, right? So sometimes it's just better to leave it at the very end. Like again, you don't know what's gonna be. Like if you can see again a few steps ahead, it's gonna help. But if you can't, it's just try and see what happens. And if it becomes difficult, then okay, maybe I should rationalize this one and then just go back and plug it in. Okay, so I'm gonna try this one without rationalizing and see what we get. So 2 times 1 over 2 square root of 2. So 2 times tangent of theta I've just done at the top of the fraction line. And at the bottom, we do 1 minus squaring the tangent of theta. So 1 over 2 square root of 2, everything squared. Now this is 2 over 1 there. So I can cancel the 2 from the top there and the 2 from the bottom there because it's multiplication in between them. So I'm going to be left with 1 over square root of 2 at the top of the fraction line. At the bottom, I have 1 minus 1 squared, which is 1. Then at the bottom, 2 square root of 2 squared is going to be remember where this one came from, right? It came from square root of 8. So if you square that, it's going to give you 8, right? Or you just do it separately, 2 squared, which is 4. Square root of 2 squared is 2. So 2 times 4 is 8. I'm copying the numerator again, 1 over square root of 2. And at the denominator, we have to subtract. 1 minus 1/8 is going to be how many 8s? 8 over 8 is going to be 1. And if I subtract 1/8, it's going to be 7/8, right? But yes, you can do 8 over 8 minus 1 over 8, and that's going to give you 7/8. Now we're going to apply what we know about division of fractions. We write the first fraction, 1 over square root of 2, and we times it by the reciprocal of the second one. So times it by 8 over 7. And we have nothing to cancel there. So 1 times 8 is 8. 7 times square root of 7 is just 7 times square root of 2 is 7 square root of 2. And here's your square root of 2 now in the denominator. Since this is our final answer, we would have to rationalize, right? So how do we rationalize? Just square root of 2 there, because it's times here, okay? Nothing really complicated. So square root of 2 at the top as well, because this whole thing you multiply by must be equal to 1, okay? Because 1 times that is still that. Doesn't change the value of your expression. And you can always use a calculator and make sure it's the same value. At the very end, in the rationalized form, just try it and see. If you're not getting the same thing, then something went wrong. Then we have 8 square root of 2 at the top, and then we will have 7 times 2 at the bottom, which is 14. So we can simplify, right? 8 and 14. 4 and 7. So 4 square root of 2 over 7 is the value of tangent of 2 theta. So these two, this one and that fraction, they're equal in value.
Do you have to use the same formula to get the final answer, or you can use
Which other one do you think you could use? Which other ones do you want to use? The one on the paper? This is the same formula on the paper. This one here? This one?
the square root over 2.
This one?
Yeah.
This is a rationalized form. So we said like you can rationalize from the beginning, or you can just rationalize at the end. So since like I think in the notes you have it rationalized over here, right? Now you have it done in 2 ways, and you can see it's still not going to affect your final answer. You're still getting to the 4 square root of 2 over 7, right? So it's really up to you, whichever is like easier for you to do. Right? I didn't think this was that easy, that hard. I mean, for the rationalization at the very end, right? So you can analyze this question in your notes and see which one do you prefer. Okay, so that was just finding exact values, and you notice that in those situations we had to use x, y, r because the angle theta was not given. So usually for x, y, r questions, you don't know the angle, and you have to use the value of a given function to find other function values. Okay, of course, in combination with the quadrants, because quadrants will tell you if it's positive or negative for your other function. Now, example 2 will tell you that we can also use these expressions, these formulas, to calculate exact value when the angles are given, but you don't have this angle in your unit circle, so you're stuck, right? So here you have to recognize the pattern of 2 times sine of an angle times cosine of the same angle. So our angle is 5 pi over 8, okay? And then you have to look at your formula sheet. And where do I see that pattern? 2 times sine times cos of the same angle. Now, obviously, you're going to look in this box because this is our box for lesson 3, right? 2 sine cos, right? So that's the one that's given to us. And I can't use it because I don't know what that angle is. It's not in the unit circle. So then I'm saying, okay, if this is not useful, how about the other side? Can I replace it and see what happens? Is that going to help me, right? So we're going to replace it. We say 2 sine of 5 pi. Let me write in the notes. 2 times sine of 5 pi over 8 cos of 5 pi over 8 is the double angle formula for sine, right? So sine of double theta. So 2 times 5 pi over 8. So here you have the 5 pi over 8 by itself. Here you're going to have it double. Make sense? Okay, so now that you have it in the double form, see if you can do any cancellation that's going to change the angle for you. And I can because I have 2 over 1 there, and 2 and the a simplify to 1 and 4. So what I will have to do now without the calculator is sine of 5 pi over 4. Well, 5 pi over 4 is an angle in quadrant 3 with theta r pi over 4. So then all I have to do is think about the sign that I will take for that value in quadrant 3. So that would be in quadrant 3, sign values are negative. And think about the value of sine of pi over 4, right? The reference angle in the first quadrant, because I didn't ask you to memorize the entire unit circle, just the first quadrant and the quadrantal angles. So negative square root of 2 over 2. Now, sometimes in your test, you may get a multiple choice question, okay? And then you do your work and you end up with square root of 2 over 2 negative. And then these are your options. Now we for sure know that those are not it. So you can eliminate those ones right away. Usually when I do multiple choice, I always eliminate the obvious not choices, okay? And then you narrow it down. So which one of these could be? B, of course. It's just not the rationalized form, right? So if you rationalize here, square root of 2 over square root of 2, you're gonna get 2 square root of 2 over 2 negative, right? And you can unrationalize this one as well. Just multiply again by square root of 2 over 2, and then you're gonna go get back to the unrationalized form. Which one in the book?
Well, you know, first one is 2 sine and cosine, so, yeah, sine and cosine is the same angle, put into one bracket.
That's right, yeah.
Just like,
So here on the right-hand side, all of these ones are single angles. And here on the left-hand side, all of them are doubles of that single angle, right? So if here you would have 15, in here you would have 30 now, because it has to be double that. Here, these are not the same angles. It's just written in terms of those single angles. Right? Because if I give it a name, if I say A is 15, now what's inside here? It's not 15, it's just double of the 15, which is 30. 15 and 30 are two different angles, right? But we can say, if we say 30 is 2 times 15, we can write it like that, but it's still a different angle. Make sense? Okay, I hope so. Let's do one more. What is the exact value of the expression cosine square of pi over 12 minus sine square of pi over 12? Again, notice the pattern. You have cos square of an angle, call it theta or A, minus sine square of the same angle. Okay, you're stuck because you asked about exact value, so you can't just take your calculator and because that's possible, okay? But since you can't, you have to use unit circle and formulas, identities. So you have to find a pattern in your identities. So which one will it be? The second one, right? And it's the double angle for cosine, right? So cosine of double whatever angle we have. This is the right-hand side again expression. So since that's not useful, we're gonna go to the left-hand side. It doesn't really matter the way you write them though, so don't get stuck on left and right, because it can just be vice versa written as well. So cosine square of pi over 12 minus sine square of pi over 12. It's going to be the formula for cosine of double the pi over 12. So double that angle. So when we double the angle pi over 12, we get to the angle pi over 6, which is an angle you know how to get values for. So cosine of pi over 6. This is nice and easily placed in first quadrant, pi over 6. So positive cosine the first coordinate of the unit circle points, square root of 3 over,
You said the coordinate.
yeah, it is in quadrant 1, yes. Quadrant 1. For quadrant 1 angles, you don't have to write that because it's already there, right? So which one is it? D. Okay, so not much more left for this unit. For this lesson at unit. It's just the other types of questions. One is proof of an identity, and the other one is sort of a rearrangement slash simplifying of an expression. So prove the following identity: 1 plus sine of double theta equals sine theta plus cosine theta, everything squared. Now, to be honest with you, I don't think I ever put a double angle identity in tests because they're so rare that you don't really need to use them. But I always think it's important to have at least 1 or 2 examples of the things that you might not get in the test, just to see that they exist. You know, can you have them? That yes, you can have them, and yes, they can be a little bit more difficult because the left-hand side involves a double angle and the right-hand side involves a single angle. So you have to find your way so that the angles that are the arguments of both sides of your equality are the same type of angle, because otherwise you cannot say they're equal unless you can prove they're equal, right? So 1 plus sine of double theta is on the left-hand side of the vertical line, and sine theta plus cos theta, everything square, is on the right-hand side. If I were to start here on the left-hand side, since the sine of double angle just goes to 2 times sine theta cos theta, I'm going to be sort of stuck there, okay? Because I already have everything in terms of sine and cos. I won't be able to do much with that. So I'm going to try to go from here and see what happens, because here I see I have something more to do. I'll square it, and then I maybe will get some like terms. I'll see what happens. Now, attention with the squaring, because squaring means squaring over binomial means you have to do distribution. So don't forget about that. That's what it means, right? If you open it up, if you open that square up, it means you have to multiply that bracket by itself. Right? So now foiling it, you have sine of theta times sine of theta, which is making it sine squared theta. So that one, and then sine times cos. Sine cos, and then cos times sine, which is again sine cos, because it's the same thing, right? And the last one, cos times cos, which is cos squared. Yeah. Sine, cos, cosine, those are exactly the same terms. They're just in a different order. Multiplication is commutative, so it doesn't matter in which order you write them. So all it means we have 2 of the same kind. So I can say I have 2 sine theta, cos theta, 2 of them. Make sense? It's like this, if this one, you say, let this one be x, well, what's x plus x? It's 2 x's, right? So 2 sine theta, cos theta. And then sine squared theta plus cos squared theta, that's what? Pythagorean identity, right? So that equals 1. So we have 1 plus 2 sine theta cos theta. 1 plus, and then 2 sine theta cos theta. That's the double angle identity for sine. So sine of 2 theta. So these two are equal. The left-hand side equals the right-hand side. So always make sure you write that at the very end. Make sure they are equal. Too easy. Simplify in terms of a single trigonometric function. Sine of 5 over 2x, cos of 5 over 2x. So we have sine of 5 over 2x times cos of 5 over 2x. Now the pattern of sine times cos of the same angle, let's say our angle is theta there. Doesn't appear in many of your identities. Appears here, sine, cos, cos, sine, but the problem is the two angles are different, right? So you have an angle that's alpha and an angle that's beta, okay? And even if you do try to use it, you're still gonna end up the same way, but you're actually doing it longer because you're proving first the identity and then you apply it, right? And don't have to do that. So you look, where do I see sine cos? Oh, there's another sine cos. And this one does go well because I have the same angle and I have the same angle. But the problem is I don't have the 2 in front of it, right? So I don't have anything in front of it. Okay, so now if this is not a 2 here, but it's a 1, it doesn't exactly, if you don't have the 2 here, it doesn't exactly equal sine of the double angle, right? The sine of the angle 5x over 2, and I missed there, so let me do that again. Sine of 2 times 5x over 2. So I can't say I can use it directly like that, right? I only have 1 here, okay? So I need 2. What can I do to make it into a 2? So I can have that equality. Well, I can't just multiply by 2, right? Because then I'm changing the value of it, right? But I can say I'm multiplying by 1, which is 2 over 2. That makes sense? So I need the 2 from the top here to use it for my identity. But then the 1/2 is going to be still in front because I don't need it for the identity. Does that make sense? Sort of, right? Again, you cannot multiply. If I say I want 3 here, or I have 3, but I need something else on the other side, so I need to multiply this 3 by 2. Okay, like you can't. You have to only multiply by 1. So it has to be 2 over 2. I can write 2 over 2 as 1/2 times 2. It's still the same thing. Does that make sense? Because I can split it up in the parts that I need. Because 2 over 2 times 3 is still 3, right? Is it clear? Now back to what we need here. We needed this 2 so we can complete our double angle identity. But when we put that 2 there, from that 2 over 2, we're left with a 1/2 in front. okay? So this half in front has to be on the other side as well, okay? Because I can't just do one half there and not do one half over there as well. So it equals to that, but this part equals to that, right? And I also have a 1/2 in front. So 1/2 times sine of 2 times 5x over 2, the 2 and the 2 will cancel out, is 5x only. So all we gotta do is just leave it the way it is, because now it's in terms of sine only. I got rid of the cosine. So it's a little bit of a clever approach to make your formula complete when it wasn't. It was an incomplete formula. But when you did that, when you completed the formula, you had some leftover from that completion, and you had to repeat the leftover on the other side. Or just think about this one. Oh, I have a 2 here. What does this equal to? It equals to sine of the double angle. And then 1/2 has to be copied in front. So now that I explained maybe a little bit too much detail there, if I were to do this again, because I think some of you understand, some of you are just about to understand. Once I analyze it and I recognize the pattern, oh, I need a 2 in front. That's not there to begin with, right? But that's going to complete my formula. I am not allowed to multiply by 2 only, right? Because it's going to change the value. It's going to double the value from before. So what's going to cancel out that times 2? The 1/2, right? The 1/2 and 2 together, it just makes sense that you multiply only by 1, so you're not changing it. Now, just convert what you have so far. You still have the 1/2 in front, and the 2 that you put there now makes up the formula for yourself, which is sine of the double of the 5x over 2, right? 2 and 2 cancels out, so it's 1/2 sine of 5x. The end. Bedtime story is over.